Hello everyone, welcome to Hydropower. Today, in this lecture we will talk about the hydromechanical equipment installation in Powerhouse, so let's start. A hydromechanical installation in a hydropower powerhouse refers to the mechanical and hydraulic components and systems that are responsible for the control, regulation, and operation of the hydropower plant's turbines and associated equipment. These installations are essential for optimizing the efficiency and safety of the hydropower generation process. Here are key components and aspects of a hydromechanical installation in a powerhouse: surge tank and pressure control, pressure fluctuations and water hammer. Surge tanks absorb pressure fluctuations, preventing water hammer effects and ensuring stable operating conditions for the hydraulic system. Protection from pressure surges. They protect the system from abrupt pressure surges, safeguarding the equipment and maintaining the plant's efficiency. Penstock and pipelines, efficient water transportation. The carefully positioned and supported penstock transports water from the source to the turbines, minimizing leakage and energy losses. Friction minimization. Special attention is given to reducing friction within the pipeline, ensuring optimal energy conversion and transmission. Penstock insulation and coatings, corrosion prevention. Insulation and coatings protect against corrosion, extending the lifespan of the penstock and maintaining its structural integrity. Energy efficiency. Insulated penstocks help preserve the temperature of the flowing water, optimizing energy efficiency throughout the entire system. Turbines and generators, hydraulic power generation. The turbines, securely anchored to robust foundations, harness the power of water flow and spin the generators, producing clean and renewable electricity. Powerhouse positioning. The generators, coupled with the turbines, are strategically positioned within the powerhouse to efficiently convert the kinetic energy of water into electrical energy. Alignment and calibration, precision alignment. Alignment specialists ensure the perfect alignment of turbine and generator components, optimizing performance and reducing wear and tear. Accurate monitoring. Calibration of sensors and measurement devices guarantees precise monitoring and control of variables, enabling optimal operation of the power plant. Inlet valves and controls, precise positioning. Inlet valves are precisely positioned at the entrance to the penstock, regulating the flow of water and facilitating efficient turbine operation. Advanced control systems. These valves are connected to advanced control systems, including hydraulic actuators and electronic control panels, allowing for precise and automated operation. Draft tubes and tailrace, water flow control. Draft tubes intricately connect to the turbines, controlling the flow of water as it exits, ensuring optimal efficiency and minimizing power losses. Optimized water discharge. The precisely constructed tailrace efficiently discharges the water, maintaining a balanced hydraulic system and preserving environmental equilibrium. Hydraulic power units and governor systems, hydraulic pressure. Hydraulic power units provide the necessary hydraulic pressure to various hydraulic actuators and control systems within the hydromechanical setup. Turbine speed management. Governor systems expertly manage the speed of the turbines, ensuring they operate optimally within the desired range for efficient power generation. Hydraulic fluids and lubrication, optimal system function. Hydraulic systems receive specific hydraulic fluids, enabling smooth and efficient operation of various components within the hydromechanical equipment. Reduced friction and wear. Lubrication is meticulously applied to bearings, seals, and moving parts, minimizing friction and wear, increasing the lifespan of the equipment. Instrumentation and control systems, precise monitoring. State-of-the-art instrumentation continuously monitors critical parameters such as turbine speed, water flow rate, and pressure, ensuring efficient and safe operation. Control and regulation. Advanced control systems allow operators to monitor and adjust various equipment settings, optimizing performance and responding to changing conditions. Control room setup, central command hub. The fully equipped control room serves as the central command hub, housing control panels, sophisticated instrumentation displays, and seamless communication systems. Real-time decision making. Operators have access to crucial data, enabling them to make informed decisions swiftly and effectively to ensure smooth and reliable operation. Remote monitoring and control systems. Advanced remote monitoring and control systems allow operators to manage and adjust equipment settings from a central location, enhancing efficiency and safety across the entire hydromechanical installation. Periodic maintenance planning, maintenance schedules. A comprehensive maintenance plan outlines regular inspection, servicing, and maintenance tasks, ensuring the long-term reliability and performance of the hydromechanical system. Preventive measures. Proactive maintenance helps identify potential issues early, mitigating risks and minimizing costly downtime, ultimately maximizing power output and reducing operational costs. Ongoing optimization. Continual improvement and performance optimization are achieved through comprehensive maintenance programs, incorporating technological advancements and best practices. Trash racks and screens intake structure protection. Trash racks and screens meticulously installed at the intake structure or penstock entrance prevent debris from entering, safeguarding the equipment and optimizing performance. Flow efficiency. These protective elements also play a vital role in ensuring a smooth and uninterrupted flow of water, enhancing the overall efficiency of the hydromechanical system. Safety systems and emergency protocols. Robust safety integration. Strong safety systems, including emergency shutdown mechanisms, are an integral part of the hydromechanical installation, protecting both personnel and equipment. Emergency preparedness. Emergency protocols are in place to handle unforeseen events effectively, safeguarding the surrounding environment and ensuring the overall reliability of the hydropower plant. Quality assurance and testing. Striving for excellence. Rigorous quality assurance processes are followed during installation, ensuring all components meet design specifications and ensuring the highest standards of reliability and safety. Thorough testing. Comprehensive testing procedures are implemented to validate the performance of the hydromechanical equipment, guaranteeing optimal functionality and operational efficiency. Environmental considerations. Environmental safeguards may be integrated into the design of a hydromechanical installation, protecting aquatic life and ensuring sustainable operation throughout the powerhouse. Compliance with regulations. Local, national, and international standards. Installation adheres to stringent local, national, and international regulations and standards, demonstrating commitment to safety, efficiency, and environmental responsibility. Ethical power generation. The hydromechanical setup complies with guidelines and protocols, contributing to responsible and ethical power generation from renewable sources. Ensuring safe and efficient operation. A well-designed and maintained hydromechanical installation is essential for the safe and efficient operation of a hydropower plant. Regular maintenance, thorough testing, and continuous monitoring are crucial for ensuring the reliability and optimal performance of these vital systems. So this much for today. We will come again with new video. Till then, keep on watching our videos. Thank you.